我把录像录着。
大小写都是沿着按照它的来的。
等会儿，在这儿是吧？那个记。因为我们之前是在Linux这儿装的，都是默认都是装完了就是空的，都是空的，没有密码。哎，你这大写是 Shift 加这个是吗？按你说应该是这个。C 可能不能粘贴，有可能。C 属是 F S。等会儿我查一下那个重新改密码的那个。Spoken about various technologies that make up the web architecture. We spent a reasonable amount of time looking at some of the representational technologies, so HTML and XML, CSS styling. We also spent a little bit of time looking at HTTP, which is one of the systems for allowing us to operate on the web, to be able to communicate on the web. That sort of underlines the fact that we have the web at all. We need that protocol for it to be able to operate the web. However, when that was originally designed, there was no formal structure for how to use that to make things, how to make applications, how to make systems that make use of the web. improve. People try things and learn from the mistakes and so on. But eventually, a guy called Roy Fielding, who was one of the authors of the original HTTP specs, HTTP 1.0 and 1.1, wrote a PhD thesis. And in his PhD thesis, he looked at the idea of structuring applications on the web and provided an example architecture, or a set of constraints and a set of principles for being able to build applications that make use of all of those bits of web technology that we've seen before in a sound way. And it's some of those principles aim to enable the cool things that you can do on the web. And we'll talk a bit about what each of those constraints allow us along the way. So his thesis is available. I'll point to it in one of the slides. There's a link to it. So if you want to go and read in more detail what his hypothesis was and how he went about discovering this, all the background that he did into existing web architectures and existing other system architectures, it's all out there. So, the first thing that we're going to talk about are the constraints that we put on this system to enable it to act in the way that we expect. We'll then talk a bit about some of the elements that make up and then we'll talk about how that applies to web services. And we'll talk about what web services when we get to that bit, but we'll talk about how REST then enables us to have a good structure for web services. So, right, what are the constraints of REST? So, what do we do to this system to enable, what do we do to the technology out there, and what do we embody in how each of those web architecture technologies work to enable us to have this architecture. These principles each have some benefits, which is why the principles are there, but they each have some drawbacks about those too. So there are five constraints that Fielding explains have to exist. One of them is an optional addition, and that's the code on demand. But the five that have to be there, it has to be client server, it has to be stateless, it has to be cacheable, it has to be a layered system, it has to be a uniform interface. We're going to go through slides that explain what each of those are. So by client server, we mean there are two aspects to this communication, and that they have different concerns. They have different parts to play within this. So the server, as in the machine that exists remotely, the one that you're connecting to when you're making use of the web, is primarily there for data storage. It's the one that has the resources that your client wants to retrieve. The client is the other piece of software, and the concern there is the user interface. The concern there is providing the person, or maybe the machine, the software that's trying to interact with this architecture, the ability to both view or access those resources, but also to operate the communication, operate the interaction with the server. And that's the job of the client. The aim here is to allow both of those two things to concentrate on that part. So the client only has to do user interface, the server only has to do data storage. The server doesn't have to be concerned with providing the interface directly to the user, and the client doesn't have to worry about storing data. It leaves that to the server. Client-server architecture, if you've not done networking courses before, is a common approach for defining the interaction between two machines. So the alternative really is peer-to-peer, and it describes a slightly different relationship in both those cases. Peer-to-peer means that the two computers that are connecting are equal in some way, and that they're communicating between themselves to share information. Client server implies this idea of something being sort of the source of a resource, the place where you go to get it, the server, and the client is the piece of software that requests that. Of course, this is an architectural thing. Some things combine both of those approaches. Some things do variations of this, and they don't quite look like client server or BitKit. But those are, like, at a high level, the two types of networking architecture. So, what are the benefits of this? Well, it allows the user interface to be portable, so it can be used in multiple places. Because the client is handling the user interface, whatever platform that client runs on, that is able to provide a user interface that is ideal for that platform. If the server has to provide that user interface, then the server would have a whole load more work to do to cater to all the variety of clients. By separating that concern, the client can take care of the bit that's relevant to it, or will be custom for it. Also, by simplifying the server, so by removing the need to do the user interface, you improve scalability. So by making the server do less things, making it have less tasks, you enable that to, you mean that each request, each access needs less resources, and therefore you can run more of this service. You can have more people access it, or more clients access it for the same cost, for the same sort of hardware power. And it allows the two things to evolve separately. So it means that the server isn't reliant on the user interface keeping up. The server would improve and wait for the client developer to catch up with that. Or vice versa, the client might be excellent, but it's waiting for features in the server. But they're not tied. They're related, but they're not tied directly. Okay, so client server is one of our key things. It's a principle of something being part of the web architecture, of it being REST, the REST architecture. The second one, stateless. The idea here being that with each interaction with the server knows nothing about what the client is, what the client has done before. So the server doesn't do anything in its direct interaction to try and identify the client and customize at that point. Now, you might then say, well, what happens when I access sites that do customize? What's going on there? The important thing to separate there is that there are two servers at that point. So the server we're talking about here that's stateless is the front part that connects to the client. We've got a client over here. And it's a front end onto something else. So this is our HTTP server. And that connects to our application server. And what's stateless is a HTTP server. A HTTP protocol has no idea for state. So the HTTP protocol will respond to the same resource regardless of the client that accesses it. It won't do anything to personalize that just because of the particular client that accesses it. You might, as part of building your system, of building your web-based system, have an application server that runs behind your HTTP that creates the resources or changes the resources based on the request from the client. But that's considered a separate thing. So there might be state in your application server, but importantly, HTTP has no state. And this is for a number of reasons again. So it increases scalability again by removing the need for the server to keep track of state. That interface, that protocol, is much lighter weight, needs less resources, allows the server to be scaled up for less cost, for less overheads. Useful here. And improved reliability, so failures within those interactions are easy to recover. So each request is in isolation. You don't have to keep track of what other requests have happened. You can just deal with each request on its own. And again, in terms of scalability, that allows you to deal with all of these without having to communicate into some central data source that interactions have come from different places. You can always treat each request in isolation. So that's stateless. You can indicate information to the, like the client can indicate information to the server. So the client can keep track of its state, the client can keep track of that information, but it then has to send that with every request. So the server isn't storing anything about that, the client has to have that information and provide it each time. And by that, like what typically happens there, that's normally where things like cookies come into play. Those are a piece of data that you send with the request that identifies something about the state of the client. So cookies exist there for the client to track its state, so the server doesn't have to. But of course that does mean that each time you do the interaction, each time you send, the client has to send that state, has to send the cookie to the server, so that the server can use access, or has to pass it into the application server. Okay, cache or cacheable. So one of the third requirement of a RESTful interface is that you create it in a way that allows resources to be cached if possible. So again, allows the client to avoid contacting the server if it's already made that same request. If the client can record that it's made the same request, the exact same request for the same resource before, it doesn't have to repeat that. It can retrieve it from its own cache, it can retrieve it from its own storage. So that makes some of those interactions quicker. It means you don't have to always go to the server for those interactions if you're retrieving the same thing. Like a good example of that you will have come across or that you will experience is that you'll browse like pages that you visit regularly, so the front page of Google or something like that, something that doesn't change and you access regularly will be cached. You get that, your computer will store a copy of that when it gets it the first time, and until it decides to expire that, until it decides that a certain amount of time has passed to be able to, that it needs to refresh that, it can go ahead and just report and like show you that one. The issue there is that you do risk the data becoming stale, you risk the data being out of date if you rely on the cache too much. Typically caching allows the server to set when that information will expire. So the server will be able to set through its headers in a response, will be able to say this is how long this information will probably be valid for. If it's after that time, then get a fresh copy. I don't know if Nick noted that in the HTTP talk, but the head request also lets you do an element of this cache checking. The head request lets you find out about the resource and find out whether it's been modified or changed without having to get the whole body of the content. So you can do a head request to reduce the overhead, and if it's not changed since you last got it or since you cached it, then you use your cache version. And we'll see this, like this becomes important when we start considering how we define our resources, our URLs, or our URIs. Because we want our URIs to represent something that could be cached. So we then need to be careful that our URIs don't do things like make modifications if we get them. Something that we just get should be cacheable as long as it's not changing regularly. So that sort of leads into the idea of not being able to make modifications with a GET request. That's why we have post as a separate verb within our dialect, within our language. REST also provides the constraint of a uniform interface between each of these parts. So between the server, the client, the various pieces of software that make this up. And this includes like some of the technologies, some of the parts of the standards that we've spoken about already. So identification of resources, URIs, that is a uniform interface amongst all of the things that work in the web architecture, and you have to use that uniform interface, otherwise you risk not being understood by systems that are on the web. We manipulate the resources through the representations, so we display our resources, we have access to the resources, and we interact with them that way. There is a encouragement to use messages back from each of these stages, so like the HTTP response messages, so that they're descriptive, so that they're at least sort of understandable. So it's not all machine understandable, so that there is an element of understanding the information. And then the fourth thing that fits into this uniform interface, and we're going to talk about this a lot more further on in the slides, is this idea, and this is sort of what, like, there are a bunch of these bits that define REST that people are very comfortable with, and are just sort of how people think about using web resources anyway. But hypermedia as the application, the engine of application state is often misunderstood, but I think is like a crucial bit of what makes REST an interesting architecture. We'll talk about it in a little while, or we'll look at some of it in a while. What it effectively means is that to combat that thing that we spoke about a couple of slides ago, that the whole interaction is stateless, the reality is that our applications that we build on these architectures need to record what's happening. They need to represent both internally and to the user what's happening, or to the client what's happening through the interaction here. And what Fielding's thesis says is that we should use hypermedia, we should use links, and the access to different things as that way of representing state and state changes. So as part of our responses, we're telling the client what state the application currently is in, and then we also provide, as part of that response, what are the next states we can get into, what are the next actions the client can take that will move them to a different state within the application. So again, this massively enables that idea of separating the concerns. It allows client servers, applications to change independently, but because they're speaking with a uniform interface, because they're fulfilling a uniform interface, they're able to still interact. When something improves, when the application improves, we don't then have to change every single client to match that, because they all communicate with the same set of standards and they all meet these requirements. It does mean that if you're following, like sometimes when you're following a uniform interface, it does mean that you have some performance hits because you're having to do all of these things, and you might choose to optimize those out if you were designing this independently, but because we're using this to enable that independent evolvability and allowing interactions between the various components, you then have some overhead within that. Okay, lastly, or penultimately, this is the fifth and final required constraint, that the systems are layered, but that each element doesn't need to know further than the state it communicates with. So that means if we have like a client that talks to a proxy server that talks to a HTTP server, the HTTP server doesn't need to know about the client doesn't need to know about the HTTP server, they just need to know about the thing they're connecting to, in this case, in this example, the proxy server, and everything that goes on beyond that is a no, like they don't need to know the information about that. And that allows us to put things in between, like caching servers, that are able to add to our system, or it allows us to add things like load balancing, where we have one point that we connect to, but actually the machine, the computer behind that services the request, can be spread amongst dozens or hundreds of machines, which increases your ability to service a large amount of requests. But again, add some latency, add some overhead, because we're introducing a bit more complex, or introducing some more levels within it. Okay, final constraint. The last constraint is optional, but it suggests that the server can extend the client functionality by sending it code. And we see this in the World Wide Web with mostly with scripting languages, so JavaScript that runs in the browser, and the server can send that to change what the client does, or to change the functionality of the client. And we saw that a bit with applets, back when applets were a thing that weren't blocked by every single browser on the planet. And this improves extensibility. It means, again, you don't have to change every client to support new additions to the spec. It means that individual applications can add their own functionality if they need to. Sometimes it means that you don't know what all those clients are going to do in advance, because it changes based on what's downloaded from the server. Okay, so brief interlude with architectural elements. Let's talk about the things that make this up, and then we're going to talk about REST. So, things we're going to talk about. So we've got the various data elements that make up the system. So we have resources and their identifiers, we have representations, we have metadata about each of those representations. So these all interact as part of our server. We have the various bits of software that allow us to connect here. So we've got things that act as clients. So we have browsers, or we have software like www. We have software that knows how to be the client side of HTTP, to do those HTTP requests. We have things like Postman that enable us to manually construct HTTP requests. We have things like curl that lets us do that on command. We have servers, so we have software that can provide responses to HTTP requests. So we can get software like Apache or Microsoft IIF or Nginx that are built to respond to HTTP requests. And there's software and hardware that will do caching, so recording of requests and the responses to those, speeding things up. And we also have software like resolvers like libDNS, and bind, and tunnels like SOX and SSL that enable us to do some of the network side of this. So resolvers help us work out from our URI what actual bit of software, what machine, what IP address to connect to. Tunnels allow us to do things like encrypt that communication if we want to. Our components are our origin server, our gateway, our proxy, and our user agent. So the origin server is what we describe the machine where this information is coming from. So this thing here, our HTTP server, in this case, is our origin. And we need to be distinct about that, because we might have other things in the way. We might have things that are layered in between this. So we have gateways and proxies. These are various bits of software that let us connect from our client to our server, to provide various various functions, and we have the user agent, which is what's the software client end. And we saw user agent as one of the HTTP headers that we were talking about when we were doing some of the HTTP communications. The user agent defines what the software is that's running the client. So this is really just sort of some of the vocabulary that we'll be using throughout talking about REST, and that you'll hear used without much explanation as you're reading about it. If you're interested in, well, hopefully you should be interested because this is a reasonably core bit of the course. If you're interested in reading more broadly around the sort of the architectural style and some of the background that led to building, coming up with the REST architecture, his thesis is online. The URL's there. You can Google for building REST thesis and you'll get to it. Chapters 4 to 6 are useful in terms of what the REST architecture is doing. Now, right, last segment, we're going to talk about this in terms of web services. Who can tell me what a web service is? Who's heard of a web service? Excellent. What is it? It has a back stayed up a bit longer. Yeah, go on.
It's a way of making an HTTP request that brings back a packet of data like XML or JSON and provides it as a service for you to use displaying data on your own website.
Absolutely. So who interacts with web services, or what interacts with the
the web application itself, and you can build say you could have a plugin on WordPress that could use Flickr's API to pull back your Flickr photographs and display them on your WordPress blog.
Absolutely. So you'll hear the word API thrown around a lot in relation to this. An API is an application programming interface, and that means a set of actions that a piece of software can take that will get it to do, or that will do some functionality on its behalf. APIs exist within like all different areas of computing, so when you're programming and you have to interact with the operating system and the file system accessing data in the current machine, you'll use an API to do that. If you have to interact on the web, or if you have to interact even just with your programming language's standard libraries, you will access these through application programming interfaces. And yeah, so a web service is a piece of software that provides, or a web service provides data accessed by the web, so accessed by HTTP, so that other machines, other programs, other applications can use that data. So it's in contrast to websites or web pages where we as a human are accessing some information and we retrieve a document or an image or other types of documents, so we get HTML documents, PDFs or so on. Those things are intended for us as humans, and we access those through our client as a web browser, and we have access, and we use we barely even touch what's going on with HTTP. We use the browser and its interfaces to allow us to do that HTTP request and to retrieve and render and show the information. However, that's not really any good for a machine. If you're writing a piece of software, sending it back to human readable, the HTTP or the rendered, the HTML or the rendered HTML won't be of benefit to that software. The software is going to have to do work to understand what's in that, because that document is structured for us to understand as humans, not necessarily for the machine to understand. And as we said, that means we retrieve the data in a format that the machine can understand. So that's when we start going back to the technologies like XML, and we saw JSON as one of the formats that sometimes come back in these services. So, where did this all hook together? Well, people were writing web services for quite a long time, using all sorts of architectures that they'd invented. But there was a strong movement and a lot of backing behind moving towards using this architecture, the REST architecture, to build these web services. Because of all those benefits that using the web architecture allows us, all the way from like the caching elements and scalability elements and uniform interface. So, how do we do that? Well, there are various ways that we can use each of those important parts of the web architecture to build a web service, and there are some best practices. The thing, or the bit of theory, the bit of work that helps us measure how well we're using the whole web architecture and all of the elements of it to make our web service is called Richardson's maturity model. And we'll see all the elements that we've been talking about as part of the web architecture. So our identification, our communication layer, and part of our representation as elements within this. But we can get away with building web services that only use part of this. But ideally, we're aiming for web services to be fully RESTful and to use the entirety of this model. So, we can define a level 0 where we use none of those really, or we don't use any of those to their strengths, and we don't use the ability of all of those. We use a single URI, so we're not using our URIs to identify different resources. Our only resource is the web service in its entirety. So we're not making use of the power of the different resource identifiers. We only use HTTP to communicate. And we'll see that we can actually use HTTP and the power of HTTP and the sort of expressibility of HTTP to do more than that. HTTP has more than just communicate with a thing or not. We'll see how we use that. And we don't use any hypermedia. And hypermedia is that hypermedia is engine, actually engine of application state, and we'll talk about how these services use that. So where might you have seen this? Other web service systems are effectively this, level 0, making use of a single endpoint, and HTTP is only a sort of transport. So XML RPC, this is libraries that allow the programming languages to execute code on a different server, but make it look like it's happening just within the local code. That's called RPC, Remote Procedure Call, and there is a web service mechanism for representing that interaction as XML and sending it over to the server that has the code on it in an XML packet, and then unpacking it, running the code, sending a response to XML. All goes with like one URI, and HTTP is only used to do that transport. So you'll do a post to it, and it will respond with some information. Most SOAP services work like this. Has anyone heard of SOAP? Let's go to SOAP. SOAP is an older web service standard. It was standardized by the W3C. It is quite verbose. You have to do a lot of work to construct the requests that you're making. These are like lots of XML that has to be in certain formats. And whilst quite a lot of enterprise systems will use SOAP as their web service interface, because they needed some structure, some standard for making web service interfaces, a lot of people rebelled against it and didn't like SOAP because of its verbosity. And plain old XML. So this is the idea that you can just post XML documents between the systems, regardless of any sort of structure or standard. So that's effectively what SOAP does, with sending and retrieving XML documents. SOAP has a bunch of sort of standardization around it to say exactly what should be sent at each point. You can do that even without SOAP's sort of structure and format. But of course, your system will only work with other systems that know your exact protocol. It's not as independent as doing something that's RESTful. So, level 1, moving up richness and maturity level. We start using one of the aspects of the web architecture to influence our web service. In this case, we start using URIs to represent all the different resources in the system. So rather than there just being a server.com/web service URI, if our web service handles, products and wish lists and so on, we then have resources to represent each of those things in our system, so, and URIs to represent each of those resources in our system. So we have a URI like server.com/product and server.com/wishlist and server.com/basket or something like that. So we have URIs to represent each of the resources. But we're still only using HTTP as transport, so we're still only getting or posting maybe, and we're still not doing anything with hypermedia. We're not returning links to take us to the next resources. We're just returning XML data about that resource. You'll see these two terms used at this level, and they scale. We do use them in the later levels, so don't dismiss them as being in level 1, so that we don't need to remember them anymore. These are important. First one is URI templates, and this is a way of describing what the format of your URI is going to be. So if we have a URI that's made up of the server name, the resource, and then some variable, something that will change for each of the different resources, then we might have a URI template like this. You'll see different people use different things to indicate the variable part. That order ID, the curly brackets there, in this sort of, and it's an ad hoc format, like there's no, as far as I'm aware, there's nowhere that anyone said you have to use curly brackets to indicate this. It's just, you wouldn't normally have curly brackets in the URI, so when you're looking at this and you see it's a template, the curly brackets indicate a URI, that it's something that will change within that. You'll sometimes see angle brackets used, you might even see square brackets used to represent that this thing is going to be replaced with something else. And when you feed actual values into this and make a real URI, that order ID might be like, that might be from 5001 or 721. It'll be some value that fits in there. And the documentation that defines this template will explain what order ID should be. So order ID is like the identifier, is the name of that variable, and the documentation will tell you, is that a number, is that a string, is it text, is it what? And it's worth noticing that the best practice arguments for using hypertext or hypermedia at the engine of application state argue that actually you don't need URI templates. Like, this is another thing that's like useful for humans. It's useful for us to look at this and go, well, this URI is going to be an order. It's going to have some sort of number here that's going to indicate which order that we're referring to. And that's useful for us, and it might be useful for developers who are building systems to interact with this web service. But if we use hypermedia to generate those links, we don't need to rely on the template. We can provide any URI, as long as it's valid within the system. We can provide any URI, and the client just listens to what we respond with. It just believes the URI we send, so we can get away from using URI templates. And there's a bunch of arguments about like URI templates, because you're giving away the structure of this. It makes it guessable, potentially makes it hackable and things like that. If you go back and look at the exposure of Moopig's 40 API, did anyone hear about that? Did anyone read about that? About a year and a half ago, someone exposed that Moopig had an API that you could basically just you could guess what the URIs were because they were consecutive numbers. So it was order 1, and you knew the next order would be order 2, and order 3, and order 4. And you could basically get anyone's order information just by looking at each of the orders. So you could go through all the different order numbers because you knew it, because it's predictable. and you could figure out, you could then go and look at the data it returned, which is a massive security flaw. And if they had URIs that were more opaque, that would have been significantly harder to do. Obviously, they should have had a whole bunch of other security systems in place as well, like authentication. So, URI tunneling, this is the idea of using our URIs as the way of sending information to and from, and sort of creating the actions. So in this case, we might actually use a URI as an action, which is bad form, but we are in level 1, we're not all the way up level 2 or 3 yet. So we're using verbs in the URI, so generally bad, but a level 1 thing, and we're providing through URI query parameters. If you've not seen this, go and look up this format. So the question mark allows you to put data that's sent to that page or to that resource when you request it. And so we're using the URI to send some of our information. It sometimes works, it's sometimes web friendly, but you've got to be very careful if the information that you're sending and the action you've got is an action, will perform some change, because you definitely don't want that to be cached. You don't want to be able to repeat that and have a change happen every time. So if you've got this, if you've got place order and we're expecting to get like the receipt from placing that order, but that affected a change and actually placed the order every time you did a get, then you lose a lot of the ability for HTTP requests to be repeatable or cacheable and so on. So level 2, we're just one level away now. Level 2, we have the same as level 1 where we have URIs representing all the different resources, but we add to that using HTTP and its methods as part of the interaction process. And typically, not always, but typically, we'll map those onto something called CRUD. Who's heard of CRUD? Okay, so CRUD is a term talked about in database modeling and database development that refers to modifications of data. So we can create data, we can read data, we can update the data, so it's not new, but we're changing the existing one, and we can delete data. And there's sort of 4 fundamental operations for the things you can do with data. And we can map them quite easily to verbs within HTTP. So we can map doing a create to posting to a particular URI, and that will create a new resource. We can do a read by doing a get from a particular resource. We get the representation back. We can use put to do updates. So put relies on there already being a URI for this resource, but we're sending information to replace that. And we can do delete to make changes, to remove that from the system. So, final level, level 3, we're still doing those 2 bottom ones. We've still got a resource for everything, a URI for every resource. We're using verbs, probably CRUD, but maybe other variants of this, to do our actions. But importantly, every time we do those interactions, part of the resource that comes back contains links to tell us what to do next, to tell us what we're allowed to do. And this is part of a thing called, I pronounce it HETIOS, but you'll see on the web like a million different ways of pronouncing it. It stands for Hypermedia as the Engine of Application State. And the idea is that the recording of what's happening within the application is part of what resource you get back, and you're also given information about what to do next, where you go next, based on the links within that resource. So that is, your resource contains both the content that it was delivering back, whatever that representation is, probably some XML that contains some data about the resource that you requested, but it also has a set of links, and this will normally be defined in like a links element within HTML, or maybe a links JSON attribute. And typically they'll also indicate types. They'll have some attribute to explain what each of the links are. So you'll be able to look at the information and say, okay, this is a link that's going to let me create a new one of these, or it's a link that's going to let me check out and purchase these things, or it's a link that's going to let me pay. And this is how the application defines its protocol. So the application you're developing as part of this web service, it uses these states and the transitions between them to represent the application work, to constitute its protocol. So in this example, which is a sort of very generic sort of purchasing service, where you can select an item, you can confirm it, put it in your basket, or check out, I guess, and then from that you can either pay or put it in your wish list, and after you pay, you ship. Each of these are states that the application can be in, and this will be represented by a resource coming back to the client, and each of the lines are the client doing a request. So doing a request for a particular URI, and that will change the state, and it will change the list of links that are available to get out of that state. So if we've just put something in the wish list, we've run the action that puts something in the wish list, the application's in the state of being in the wish list, and the things that you're allowed to do to get out of the wish list are the lines that come out. So we can pay or we can select. And that means as part of that resource, as part of the wish list resource that comes back, the only links it provides are the ones that you're allowed to do to get out of that state. It will provide a URI for paying for this, and it will provide a URI for selecting, and it will probably tell you which method you're meant to use for that as well. And this means your client doesn't actually need to know anything about what any of the states are or what's going on. It just needs to read the response. It reads the response, and then it's got a list of links that it can go to next. And it can provide those to the user or to the as part of the interface to decide what to do next. And as they do those, it will run those, it will do the HTTP operation to go in each of those directions. Then look at the new resource and display the options out of that state. We're going to talk a bit more about this tomorrow, because we'll look at it in practice. We'll look at a couple of REST services, hopefully trying to fit together like where HTTP are very